Hello, let's talk about transistors. We have talked about resistors, capacitors, inductors, and diodes, which are four very common passive elements in circuits. And now we're going to talk about transistors. Transistors are called active elements because they help the engineer, the operator, the circuit to close and open the flow of electrons and the flow of voltage, the flow of power, pretty much like a valve in a mechanical system for water, for oil, kind of like a faucet. So transistors are key components on circuits for controlling um, objectives. So the goal of this lecture is to understand the behavior of a circuit when this transistor is implemented. Since the transistor is an active element, circuits with transistors are called active circuits, and they are also known as electronics, microprocessors, processing units. So transistors are a key aspect of electronics, of circuits, because with transistors, we can control the flow of power, the flow of information, etc. The other objective is to identify the different types of transistors and diodes, um, because transistors are a set of diodes configured such that flow of current can happen in one direction. So the second goal is to understand, to identify different types of transistors in industry. So first thing, how does a transistor work? When we talked about diodes, we noticed or we learned, we understood that diodes are based on semiconducting materials that are chosen, designed to have a configuration where one semiconductor material, say silicon, has one extra ion that can flow to phosphorus when a semiconductor material with one ion less than silicon. So whenever there's power or electric current through them, this ion will flow through here. And of course, there's multiple atoms of silicon, billions, so that there's going to be flow of current, controlled flow of current from one element to the next. Now, that was for the case of diode. When we have a transistor, what we have is a sandwich of negative and positive types. So the NPN transistor is a sandwich where the outer portion of the system is negative type, and PNP transistor is the sandwich where the opposite sides are the positive types. So that's helpful because depending on your circuit, it could be normally closed or normally open. That means that usually when you install a valve, you want it normally closed so that there's no water going through it, correct? Because if you have a valve that is normally open, then every time you see it, you will have to close it every single time. And but normally it will open by itself. That's not very useful. But in electronics, you do want sometimes you want circuits that are normally open so the power can flow through it, and you want to close it with a signal from the base that will close the flow of electrons. So you will you will control the flow and then say, when it's closed, the motor will stop. Okay, so the basic construction of a transistor is a base, where is the controlling part. In the example right here is this handle, the collector, and the emitter. Okay, so when see if it's normally closed or depending if it's normally open, when there's flow of current through the base, there's going to be an actuating current here, and then it will allow the flow of electrons through or flow of ions through the system. So the main three things to remember are that they're NPN and PNP transistors, and that the parts of a transistor are the base, the collector, and the emitter. That is the key point that I want you to remember. Now, we mentioned that the bipolar junction transistor, also called BJTs, are either made by using the NPN or PNP. We'll see the difference. The difference is that um, the diode is located at the emitter versus the positive, negative, positive, the diode is located at the collector. So that's just preference or design purposes or cost, or that's the operator or engineer decides what BJT transistor we use with bipolar junction transistor. There's a second type of transistor that is called field effect transistor, FET or FAT. And even though the concept is the same, meaning that it acts like a drain, like a valve, the difference is on one hand, the names are different. Instead of base, we have a gate. Instead of a collector, we have a drain. And instead of an emitter, we have a source. So that's one of the main differences. Also, the pretty important difference is that the symbols are the same. If you see these things on a drawing, then you should know that A, they are transistors, and B, they are different types of transistors, either BJT or FAT, depending on the symbol. And once you see the symbol, you can remember or you can talk about the element by the name of base, collector, and emitter. Those are the terminology concepts that you need to remember. For the FET, you have the gate, the drain, and the source. There's another key difference, and is that the BJT is actuated by current, because remember you have the semiconductor materials that will allow the flow of power once an ion, a charge is introduced at the base, but the FETs are based on voltage actuation. So if, evidently, pretty much like a valve, this part right here shows that the valve is off, right? Because it's perpendicular to the pipe. If you were to move this valve to be parallel with the pipe, will be 100% open. So somewhere in the middle will be metering or controlling the flow of liquid or gas. Same thing with the base and the gate. Depending on how much biased forward current you input, the flow of current through the pipe, through the emitter and collector, will have a certain range. If it's to its saturation region, at saturation point, then all the current available through the transistor can go through. If it's just a percentage of the forward current, then a percentage of the flow will go through. Similarly with the gate, this voltage potential will open 100% or some percentage so that flow of electrons or current can go through the FET. So, using the same analogy of a transistor, with a um, versus a valve, a mechanical valve. The saturation point is the point where the transistor is 100% on, and there's an open valve. Basically, we have the valve 100% open for the flow of current. When we have a cutoff is when there's no bias current or no, well, for the BJT, for the FET, when there's no voltage potential and the system is off, and it's just like closing a valve. And there's an active region, which is partially on, a little bit of flow of current can go through because it's not 100% open. This is just a partially closed or partially open valve. So, as we mentioned, the BJT has the combination of doped materials by layers, and very commonly because of cost and efficiency, you would have silicon and phosphorus for those materials, and you have your base, your emitter, and your collector. The amount of current through the base, basically this is what the controller will actuate. You send from your controller, from your Arduino, from your PLC, from wherever, you send 5 volt DC or 3.3 or whatever, depending on the type of transistor that you get, because there are different specifications. But you get, of course, I'm saying you send this from your power source, and you have to install a resistor so you get the desired current to be able to activate your transistor here. And you can put it into the saturation region to let all the flow of current here. Say this is a motor that is taking 1 amp, then even though this could be actuated with, say, 100 milliamps, then you can have a 1 amp going through this for a motor, and then you can later compute your gain and your efficiency, etc. So that's the BJT type of transistor. Remember that the other type of transistor, which is the FAT, will use the voltage between the base, the emitter, and the collector. Okay, so when we talk about BJTs, transistors, the voltages through it, remember the current is what activates the gate to open or close, but evidently voltage and current are coupled by Ohm's law. So you also have a voltage at the base, a voltage of the emitter, voltage of the collector, and the voltage between the points are in a specification page, or the manufacturer will present the voltage with BE, with the combination of the letters BE and CE. Obviously, the voltage between the collector and an emitter will be greater than 0 because the potential of the current is flowing from the collector to the emitter. Okay, so when you place your voltage, when you place your transistor in your circuits, be careful that this voltage is not extremely high, that is the voltage rated for the application, because if you get a voltage of 400 volts, but really the voltage of the transistor is rated for 40, then this will cause a hazard and will probably break, or it will cause a shortcut, etc. Now, you might ask, how can I use this in a circuit? Well, so in electromechanical circuits, you would probably have a motor up here where you're going to use a transistor to close and open your control your motor for motor on or motor off. So evidently this is going to be connected to your collector voltage. And this is going to be placed to a resistor and then placed to a ground, a shared ground, or whatever it is. So if you want to control your motor, electric motor, you can use that with, well, of course, a switch if you want a person every time to push a switch to actuate the motor, or you can use a transistor. Important point to remember: once you decide to control your circuit with transistors, you have to set up by all the things that we've been learning about Ohm's law and parallel and series resistors, and with passive elements, etc. We need to know how much current is going to the base and what is the voltage going through my transistor. Because if the voltage is too high, it can damage the transistor. And if the current is too high, it can damage the transistor. And that's why you need to place all these passive elements such as resistors and capacitors to be able to provide the right amount of current and voltage. So looking back to a transistor placed in a circuit, the cutoff mode is basically when the transistor is completely off, the circuit is open. Imagine the valve being closed so no water goes through the pipes. So the transistor is fully off when there's no forward bias going or no voltage actuating the circuit. So the 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 method to actuate the circuit is by a forward bias current. We talked about that. But when the circuit is open, the transistor acts like open circuit where the voltage coming into the base point is less than the threshold activating voltage, which this threshold voltage is set by the manufacturer of the transistor. When you buy a transistor, it will tell you on the specification page what is this threshold voltage. We mentioned that for common silicon phosphorus transistors or diodes, this is going back to the diode operation. You have a curve of voltage, current, and this voltage, activating voltage here is 0.7 volts. Okay, so if the voltage at the base is less than 0.7, this will always be open. Okay, and once you go above 0.7 volts, this will go this will open. This will close the circuit, but you have to set up your resistors and the rest of your circuit. So this current here is low, is provided to the standards of the manufacturer recommendation, but this current will flow through the transistor and will activate the transistor within the semiconductor layers. So when the voltage is less than the forward bias voltage, the transistor is not going to be operational. It will be protecting the circuit, it will be off. And whenever it's greater than 0.7, it will let current through, and then the transistor will open the gate and it will let current through to activate the rest of the system. The active mode is, remember, is the partially on mode. It's like a valve that's partially open, and then it has the gain coefficient. So if you go have your transistor and we said that here we have 1 milliamp and there's a gain of 100, that means that 100 milliamps can flow through the collector to the emitter, and the emitter current is base plus collector's current, which is equal to 101 milliamp. Okay, so there's a gain of 100. Remember that is the opposite. For passive elements, usually the output current or the output power will be less than the input power. In transistors or active elements, this is the magical thing of semiconductor materials and transistors and amplifiers, that the output has a gain, in this case is 100%, 100 times larger than the input. So this is the activating current, okay? Now, if it's 100 to 200, then this will be 200 here, and then the emitter will be 201 milliamps. And that's what we just saw. The current gain has the ratio of the current at the collector by the current at the base. And usually, depending on the manufacturer, it's Texas Instruments or whoever has beta or HFE are the common methods used for gains. And this happens once your forward voltage is larger than 0.7 volts for a silicon phosphorus semiconductor, or this one is still the NPN. And this can vary significantly. So depending on the transistor, you can have different gains. You would have to be careful when you buy it. Now, this changes with operating conditions because depending on your circuit, depending on your load, depending on your inputs, you can vary your current significantly. That's why temperature is a huge deal in circuits, because if temperature increases, then the circuit becomes less efficient, and instead of 1 milliamp, you can provide 0.6 milliamps. So the operating conditions affect um, the performance. As we said before, if you still have a gain of 100, but now your base current is 2 milliamps, then the collector would go up to 200 milliamps, and the emitter will be 202 milliamps. And this is just a review that in the NPN, which is what we've talked so far, we have the base, collector, and emitter. But in the PNP case, the flow is reversed because of the positive type being on the outer side of the sandwich. So we have the emitter and the collector letting the current flow, and is the base current that is actually be outputting, not inputting. So the operating modes, as we mentioned, are the cutoff, the active region, and the saturation region. Cutoff is when the circuit is open. Active is proportional at some point. It is more or less open to let the current go through. And saturation is completely open, completely a closed circuit where the maximum power can go through. These are the different types of symbols for the NPN. I remember by not pointing, so not pointing in is the NPN, and the PNP is the one that is pointing in. Okay, so in the NPN, you have a potential between VCE, emitter collector, and similarly in the PNP, you have a potential as well, except for the current can go through the base, because in this particular case, the current flows through the emitter first. So it's reversed. PNP, the collector is up here with a positive polarity. In PNP, the collector has a negative polarity. We also mentioned that in the active mode, the way to calculate the emitter current is by adding up. The collector has a gain, and in this case, the PNP, the current goes through the base, but since it has an opposite polarity, the bias voltage has to be negative. So BE, the voltage between the base and the emitter, now is going to be negative 0.7 volts. Okay. So in the active mode, the current flows towards the collector. The current flowing into the emitter terminal equals current to the base and collector, and current flowing to the collector flows the linear relationship of the gain coefficient. The saturation current, when the PNP gets saturated, it can act like a short circuit. Okay, so it's basically going through um, with no restriction. The current, I mean. So to review, the operating mode for NPN, this is negative, positive, negative. In saturation, the voltage at the emitter is less than the voltage at the base. Remember the NPN, the symbol is base, emitter, collector. So voltage at the emitter is less than the voltage at the base, remember, because this one is 0.7 volt difference. And the voltage at the base is larger than the voltage at the collector. So in other words, the voltage at the base is the largest. For PNP, the voltage at the base is the smallest. The active region for NPN, the emitter voltage is less than the base and is less than the voltage at the collector. For the PNP, the voltage at the emitter is greater than the voltage at base and greater than the voltage at the collector. The cutoff or the off point, the NPN has a voltage at the emitter that is greater than the voltage at the base, but less than the voltage at the collector. So in other words, the voltage at the base is the smallest voltage of all, and the PNP, the voltage at the base, is the largest voltage. So that's a good rule of thumb, a good table to have handy when you have to create a circuit to control electromechanical systems. So this is an example of what common types of transistors that we can use, that we can buy for industrial applications. And we have the 2N3904. Different manufacturers make this one. This is a pretty common transistor. It has a voltage difference of 40 volts, so it's a pretty big difference. Okay, and in this particular case, I'm going to show you in the NPN column different specifications. We have the BC547, BC337, the TIP29, and the TIP3055. So the voltage between the collector and the emitter is 45, 40, and 60. So they're pretty significant values. And the interesting thing is, look at the small current. We have a pretty high voltage. 45 volts is pretty high, but we have a very tiny current. The voltage at the collector is 100 milliamps, 800 milliamps. Well, on amp, that is dangerous current now, 15 amps. So this one so far could be used for a motor, a DC motor, for example, or an AC motor where you reduce the voltage to 60 volts. And the power dissipated is 500 milliamps, 625 milliamps, 2 watts. Look at this power, and 90 watts. This is like a light bulb. It's pretty high wattage. Okay. Now the maximum collector current, the power dissipated is equal to the input at the collector times the voltage from the collector to the emitter. Okay, so the voltage from the collector to the emitter in this case is 0.2 volts, and the current at the collector is 200 milliamps. So if you multiply V times I, that gives you units of watts, and that is 40 milliwatts. Okay, so this is how you connect the computed power dissipated. So here we have some examples. This is the controlling signal. We have to tune the signal with the resistor, so we have the input current that we want for an NPN transistor. Then probably here we can add another resistor if we needed to, and then we have a motor with a diode. Remember that when you install a motor, you probably want to have a diode because a motor has inductive responses, and we don't want any current to linger or to move, travel around the motor in the opposite direction. So that when you install a motor, you're usually going to install a diode in parallel. So this is a very important rule of thumb. And we're going to have a DC motor, so 6 volts are going to be operating the motor. Okay, So we can control the motor by turning on, off, or metering the velocity, the power of the motor with NPN. So if this is with an NPN transistor, if this is a DC voltage, we can vary the velocity of the motor, the RPMs, with voltage. In AC motors, we cannot do that because they're worked by induction. With AC, we do vary the velocity by varying the voltage. So we can actually use this to control the motor also. So if we want to turn the motor off, we simply have the cutoff region, and in this case, if we have no current going through, this will be normally open, the motor will be off. If we want to turn the motor on, we'll activate the transistor and it will shut the circuit, will be saturated, and then this will act like a short circuit. It will pretty much activate the motor. Now, in order to activate the transistor, we just have to provide the 0.7 voltage, the forward voltage for the transistor to be operating. And it's because if you remember again, we have the voltage current chart where the transistor has this 0.7 threshold to let the current go through. So once we surpass 0.7 volts, this starts operating. Of course, if you go to 3.3 or 5 or whatever, then this will be shutting down. The point is that you don't want to go too high current or too high voltage, because if your transistor is not big enough, you can damage it. So let's do an example right here. Say you're gonna use Arduino or some controller for controlling a motor. So this is gonna be a motor right here. And the motor has a resistance of 100 ohms, okay? So if you have 6 volts controlling the motor, and you know that the transistor you're choosing has a saturation voltage of 0.2 volts being used within the transistor. This is between the collector and the emitter at saturating conditions. We know that off the bat that by using this transistor, we're gonna have 6 minus 0.2 or 5.8 volts that we can use. The positive thing is that we can control the motor with a transistor. The negative thing is that we lost 0.2 volts. Okay, so now our maximum voltage that we can use is 5.2 instead of 6 volts. So the current that goes through this motor resistor is going to be 58 milliamps. Okay. Now, for a PNP example, we're gonna have the opposite configuration, because now we have the voltage going through our collector and through our emitter, and our collector is connected to the motor. So we know that we need 0.7 volts to activate the transistor. This is both for PNP and for PNP and NPN. But the problem is that we won't have the 5 volts anymore. In other words, remember that the easiest way to remember these things is normally open and normally closed. For the PNP, this could be thought as a normally open switch. In order to shut down the voltage, we have to provide a voltage that is high enough that goes to, say, 5 volts. But if you are using Arduino or some voltage that you can only get at 3.3 volt as the high or the maximum, then you cannot use this configuration, because your maximum voltage is said to be 5 volts, where you can only provide 3.3, and so you're only providing enough voltage to actuate it. So the point of this slide is to mention that this is one of the most common mistakes that people do using transistor in circuits, that they don't remember the difference between NPN versus PNP. and they buy any of them because of the cost or because of the footprint and the brand or whatever, and then they install the transistor in a circuit assuming that is one or the other, where it's not the case. That's why the NPN is so common, because it's very intuitive to install, where you have a very small voltage to activate, 0.7, and then you have your maximum voltage going through your um, your circuit, your transistor. Now, in this particular case, you have 5.8 divided by 100 internal resistance from the motor is 5.8 volts, and 5.8 volts will generate 58 milliamps, and this is well under the 200 milliamp threshold provided by the manufacturer if you look at the table that we just mentioned. So you pick one of those, and then you can use an NPN transistor for your electromechanical systems. Thank you.